Hello everyone. Let us discuss about the Gauss divergence theorem. If f vector is a vector point function, finite and differentiable in the region or bounded by the closed surface S, then the surface integral of normal component of f vector taken over S is equivalent to the integral of divergence of f vector taken over V. That is the formula double integral s f vector dot n cap into ds equal to triple integral over v del dot f vector into dv, where n cap is the unit vector in the positive outward drawn normal to s. So which is implies that it is nothing but Gauss divergence theorem. um, Surface integral is equivalent to the volume integral. Simply say surface integral is equivalent to the volume integral. Surface integral is double integral, that is the surface integral of normal component of f vector, that is the surface integral of normal component of f vector over the surface S is equal to the divergence of f vector over V volume. Okay, we have to see the first example. Verify Gauss divergence theorem for f vector equal to 4xz I vector minus y square j vector plus yz k vector over the cube x equal to 0 comma 1 x equal to 1 y equal to 0 comma y equal to 1 z equal to 0 comma 1. We have see the solution by Gauss divergence theorem. The formula is surface integral is equivalent to the volume integral. We have considered the RHS del dot f vector. So del dot f vector is del is described as dou by dou x of I vector plus dou by dou y of j vector plus dou by dou. So del dot f vector is given f vector, multiply these two dot product, which is implies del dot f vector equal to 4z minus y. So from RHS triple integral over v del dot f vector dv, that is triple integral over del dot f vector is 4z minus y and over the volume dv. So dv is dx dy dz, which implies that substitute the integration, so we get this value 3 by 2, which is the equation number 1. Next, let us taking LHS surface integral double integral over s f dot n cap ds, which is equal to, so totally cube have a 6 faces, so adding the 6 surface, which is the total surface from surface 1 double integral s1 plus surface 2 plus surface s3 plus s4 plus s5 plus s6. So we have to find the solution of double integral over s1. In surface 1, the facing equation is x. So surface, what are the points? A, B, C, D is the surface 1. So n cap normal component. In the surface 1, normal component n cap is, so this is the surface ABCD, surface 1 towards x direction, that is I direction. So normal component is I vector. ds means rate of change of surface, so the rate of change of surface towards x direction. So x direction means the another two directions are rate of change of values, that is dy dz, which is the rate of change of surface dy dz. So in surface 1, the phase is abcd at the point, so n cap is I vector, ds is the rate of change, that is dy dz. Phase equation x equal to 1, which is the s1 surface 1. Similarly, we have to see the surface to s2. The points are o, e, f, g. This in surface 2, what are the points? O, E, F, G. Backward direction. So minus I, n cap is minus I vector. Similarly, ds is rate of change dy dz, and x equal to, from the value of x is 0. From beginning, the x value is origin 0. Similarly, we have to conclude S2, S3, S4, S5 and S6. From S1, f dot n cap is given. So write f dot n cap into ds is dy dz. So f dot n cap is, f vector is given, f vector into n cap is I. So multiply dot product, I dot I is 1, another values are 0. Therefore multiply I dot I 1. So it is the coefficient of I is 4xz. So for next line, double integral over 0 to 1 4xz dy dz. Here the x phase equation x equal to 1, so 4z dy dz, which implies that 2. Similarly, we have to find s2, s3, s4 and s5. So we have adding this 6 surface equation, we get the value 3 by 2. From beginning, RHS is the value 3 by 2. Similarly, LH is the value 3 by 2. Therefore, from equation 1 and 2, LHS equal to RHS. So hence the proof. It is the another example of Gauss divergence theorem. So next example we will see in next video. Thank you.